foreign friends. Now, as usual, let's begin with the standard announcement. So if you'd like to subscribe to our mailing list, you can send the word webinar either to our email or to our WhatsApp number, which you can find on the chat bar. You can also check our calendar of future talks and all previously recorded talks on our YouTube channel. You don't have to subscribe to the channel. You don't have to like the videos because we don't care. But we do very much wish you to watch the talks and benefit from them. It's been a great stretch this year and lots of great material there. Today, we're happy to have Asun Jiménez from UFI telling us about isolated singularities of elliptic linear Weingarten graphs. Let me also clarify that Asun will not be able to see you, so please do interrupt. Let's agree that it's okay to interrupt, or if you're too shy, you can type in your question on the chat bar, and I will convey the question to her. So Asun, you have the floor. Can we do 50 minutes, stop at 5 to 3, and for questions, okay?
I think I can, yes. Thank you very much, Enrique.
Cheers.
Thank you, everybody. I'm so happy that I can be participating of this webinar. I apologize if there is any interruption of my baby child crying or something like that. As Enrique said, please stop me anytime you have any question. The point is that I'm just looking at the screen where my talk is, and I'm not allowed to see the chat. Also, if there is any problem with internet, if you can't see anymore, please text me or something like that, because I can be speaking and I won't see everybody is not here. So thank you very much for the invitation. This talk is based in work joined with my friend João P Santos from University of Brasilia. And let me start showing you how this talk is going to be. First, I'm going to do a brief introduction about geometric PDEs. In particular, we will talk we will see how elliptic linear Weingarten surfaces are related with Monnier-Pair equations, and talk about isolated singularities that may appear in these geometrical PDEs. After that, the first result I'm going to show you is a removability result. There is a result that tells us when you have, under what conditions, if you have an isolated singularity in elliptic linear Weingarten surface, in fact, you can say that this singularity doesn't exist. So the surface is regular, in fact. After that, we are going to do a study of the behavior of the unit normal of the surface close to a bad point, close to a singular point. After that, we will show how can we construct singular solutions of this elliptic linear Weingarten equation. And finally, when we put everything together, this construction procedure and the asymptotic study we have been doing before, we can state a classification result, and if we have time, also some final remarks. I will start telling you, most of you must know what is an elliptic linear Weingarten surface. This is a surface in R3 that has this linear relationship between the mean curvature and the Gaussian curvature. Here, A, B, and C are constants with this elliptic constraint that makes the solution to be elliptic, or the word elliptic comes from this relation here. Observe that in this family of surfaces, constant Gaussian curvature when we put A equal to 0, or constant mean curvature when we put B equal to 0, are containing. So this is in some sense a generalization of constant Gaussian curvature and constant mean curvature and surfaces. An important fact and simple checked fact that we are going to explore later is that if you start with an elliptic linear Weingarten surface and you do a parallel transport, normal translation, and you construct a parallel surface of your original surface, what you obtain is a new elliptic linear Weingarten surface. For instance, if you start with a k equal to 1 constant Gaussian curvature 1 surface, and you translate a distance 1 from one side and 1 to the other side, you will achieve two surfaces of constant mean curvature equal to 1/2, and so on. In the middle, you have a one-parametric family of elliptic linear Weingarten surfaces. Eventually, singularities will appear, but we will treat that later. So the point is that if you have a graph which satisfies this kind of relation here, automatically the height function we will call z of the graph will satisfy this not too friendly equation, which is a Monge-Ampere equation. Here we have a determinant of the Hessian that we obtain because we have a constraint involving the mean curvature, and we have this quasi-linear part that comes from the restriction on the mean curvature. So this Monge-Ampere equation here is part of a more general family of Monge-Ampere equations, which are called general elliptic Monge-Ampere equations. They are in general in this way: the determinant of the Hessian of a function plus a symmetric matrix A that may depend on the coordinates, the solution, and the gradient is equal to a positive function here. Well, in dimension 2, this equation can be written in this more friendly way. And this equation that originally appeared related to optimal transportation problems is in fact related with many geometrical problems that I'm going to show you in a moment. For instance, consider the simplest case when A, B, and C, this quasi-linear part, is equal to 0. So you have what is called pure Monge-Ampere equation, determinant of the Hessian equal to a positive function. If you consider this function on the right equal to 1, that is the simplest function constant that you can consider, you have the Hessian 1 equation, which is a equation that appears in many situations in differential geometry. For instance, it is related to minimal surfaces, to flat surfaces in hyperbolic space, affine geometry, and so on. And other familiar equation is when you put on the right a certain function that you can consider as a curvature, a prescribed curvature function, k, and this quadratic part here. So if you solve this equation, observe that if you solve this equation, what you obtain is a graph with this value for its Gaussian curvature. So that's why we call that prescribed curvature equation in R3. Well, what we are interested in isolated singularities of this kind of equation, particularly of elliptic linear Weingarten. So what can we say about isolated singularities of these geometrical PDEs? In some sense, for the quasi-linear case, we cannot say a lot of stuff because this is in some sense the trivial case. It happens that whenever the solution is smooth enough, close to the singularity, at the end you won't have a singularity. The singularity will be removable. This is the case, for instance, I want to show you here the simplest case, the equation for a minimal graph. We have in this case the burst theorem that says if you have an isolated singularity of this equation, in fact, this singularity doesn't exist. This is true not only for minimal graphs, but also for more general equations as prescribed mean curvature equations in more general ambients as killing vibrations and more general cases. However, if we let the equation to be more complicated, and that is the case of Monge-Ampere equation, which are fully non-linear equations, the equations are more complicated, and so more complicated solutions may appear. For instance, in the simplest case, that is in the case of determinant of the Hessian equal to 1, we can have solutions which have an isolated singularity. This is a rotational example of this. Also, I want to show you here an example of a peak sphere that is a surface of constant curvature equal to 1. You might recall the equation of prescribed curvature I have shown you before, and two symmetric singularities. This is like a American football ball. Okay. Well, what is the kind of result we want to achieve? What is our inspiration? Our model is the following result concerning pure monopole equations. Suppose that you have an equation like that, determinant of the Hessian equal to a positive function. So we proved in 2014 that if you prescribe a point in the space R3, and you consider these two classes here, M1 will be the class of solutions of this monopole equation, which have an isolated singularity at this fixed point. And we call M2 the class of regular, real, analytic, strictly convex Jordan curves in the plane. You can see in this M2 as a class of strictly convex tangent cones. Then the map that sends each surface into its limit gradient, will establish a one-to-one correspondence. That is, for each strictly convex tangent cone and each curvature function that you prescribe, each function here, analytic, you will have a unique solution, and conversely, for each solution, you will be a unique tangent cone. Don't worry about this C2 appearing here. This is a matter that this is just concern the orientation of the curves. You can ignore it. So this is the kind of result we wanted to prove, or something similar we wanted to do with elliptic linear Weingarten surfaces. I must say that this result, in fact, is a generalization of previous result in the area, as the one of Aledo, Chavez, and Galvez in 2007 concerning the Hessian equation. And for the case of constant Gaussian curvature, the work of Galvez with Pablo Mira in 2011. Recall that here the curvature can be any analytic function. However, recall that the elliptic linear Weingarten surface has satisfied a general monopole equation, an equation in this way here. And for this kind of equations, which are more general, where we have these extra terms here, this kind of previous characterization, this classification resulting in terms of strictly convex tangent cones cannot be possible at all, because we have some counterexamples. For instance, we know that there exist solutions of this kind of equation which have the singularity a limit gradient which is convex but not strictly convex. This is a counterexample. And also concerning the kind of surfaces we are going to talk about today, elliptic linear Weingarten, we know that some singularities, cusp singularities may appear, that is singularities where the gradient of the solution become the slope of the solution become vertical, so the gradient blows up. So if the gradient blows up, we won't have a tangent cone here. So we cannot expect the same type of classification for the general monopole equation. However, I must say that for special cases here, geometrical cases, as for instance, convex surfaces in warped product ambients, they satisfy an equation in this way. And for those surfaces, you do have a classification in terms of strictly convex curves. Well, what is the type of classification that we are going to obtain at the end of the talk? Will be, broadly speaking, something like that. Most of the terms here I haven't introduced yet, but you can understand. If you assume that the limit unit normal, you don't have a well-defined normal of the singularity of your surface, you only have two possibilities. The first one is that your surface is a rotationally symmetric cusp, as the one I have shown you before. Or, in fact, you will have a strictly convex real analytic curve in one of the hemispheres of the sphere. And as in the result for pure monopole equation, this these surfaces are classified in terms of their asymptotic behavior. So if you prescribe the behavior of the normal or the singularity, you will have a unique solution and conversely. So in some sense, there is a similar classification that we obtain for elliptic linear Weingarten graphs. Well, let me start with some preliminary results that we are going to need to develop our theorems here. Recall that we are talking about an elliptic linear Weingarten graph, which satisfies an equation in this type with these ugly coefficients here, and we are going to assume that the solution is defined in a certain disk minus 1 point at which we are going to place the singularity. So it's something like that. You have a disk, you have a graph, but this is at this point at the origin, you don't have a nice solution. In the sense, we used to say that a solution of the equation has an isolated singularity if the solution is not C1 at the puncture. We will call nu here. I don't remember the name of this letter. Never remember. I think it's me, whatever. This blue letter. Me will be, no, I think it's no, will be called as the limit unit normal. That is the set in the sphere that we can attain when we approach the singularity with points of the surface. So here in the graphic, you can say that the limit unit normal of this rotational surface is a strictly convex curve, okay? Well, an important tool that we are going to explore during the talk is what we call as the associated Riemannian metric to the solution. In this case, this metric can be defined for a general Monge-Ampere equation, but in the case of elliptic linear Weingarten, this quadratic form, in fact, has a geometrical meaning. It is A times the first fundamental form plus B times the second fundamental form. Since the equation is elliptic, recall that we have a constraint on the constant. This quadratic form is positive defined, but in particular, you can change the orientation if necessary and eventually change the sign of A. And so at the end, you can always assume that you have a Riemannian metric here. This will be very important next. So up to normalization, we can suppose that the constant here on the right is equal to 1. So we will deal with surfaces satisfying this linear relation here, 2a h plus bk equal to 1. And moreover, I want to let it clear that we assume that a is different from 0 in all the computations, because the case when a equal to 0 correspond to constant Gaussian curvature surfaces, and this problem had been already solved. Okay. Then we are going to consider conformal parameters u and v with respect to this new Riemannian metric, which is a times the first fundamental form plus b the second fundamental form. That is, we will write this metric in this way. This is the conformal. Lambda will be the conformal factor. Observe that by uniformization, since our original domain is a puncture disk, this omega will be an annulus, a certain annulus, or the puncture disk. So these two options will be very important, as we will see in a moment. Another important fact is that the determinant of the first fundamental form is related with this conformal factor, and because of this relation here, we see that the first fundamental form degenerates if and only if this metric ds squared does. So we can associate the degeneration points of both of them. Moreover, these conformal parameters are important, since if we reparameterize our graph now in terms of them, we write our graph as x, y, and z all in terms of u and v, the Gauss map becomes a harmonic map into the sphere. That is the Laplacian of the normal satisfy this equation here. This will be very important. And moreover, we have a representation formula in terms of the harmonic Gauss map. You can recover your elliptic linear Weingarten surface if you start with a certain harmonic map into the sphere. Maybe singularities may appear, but for each normal you have a unique surface. Well, another important tool will be doubly orthogonal parameters on the surface. That is, if you parameterize the surface with respect to lines of curvature, it turns out that these parameters are also conformal for this special metric ds square. And if you do that, a certain angle function C appears. This angle function will be positive if the surface is regular. It will vanish at the singular points. And the conformal factor of the metric ds square is related with C in this way. If C is equal to 0, you see that lambda is equal to 0. This angle function satisfies this sine-Gordon equation, which is essentially the Gauss equation of the surface. And this C here is a constant. It's a constant depending only on the constant of the linear Weingarten relation A and B. In particular, if A is equal to 0, that is when we are living with constant Gaussian curvature surfaces, this constant C here is equal to 0. That's the classical sine-Gordon equation for constant Gaussian curvature surfaces. We can also write the mean curvature and the Gaussian curvature of the surface in terms of this angle function. And you see that when C goes to 0, that is when we have a singularity, also both the mean curvature and the Gaussian curvature must blow up. So my singular point will be a point where the Gaussian and the mean curvature will blow up. Moreover, since we have some curvature estimates for elliptic linear Weingarten surfaces, we know that when the curvature of the surface blows up to plus infinity, then we have a constraint involving the constant A and this constant C that appears here. They are both strictly negative. And conversely, if the singularity is concave, then A and C must be positive. This will be important in a minute. Okay, so let me state our first result, which is a removability result. Before I write it here, let me start with a definition. We say that an immersion from a puncture disk into the Euclidean space has an extendable singularity at the puncture, at the origin in this case, if the map X and the normal of the immersion extend smoothly to the whole disk. And moreover, if the singularity will be called removable if it is extendable and also an immersion at the puncture, at the singularity in this case. So with these two definitions, we can state the removability lemma. It says that if you have an isolated singularity, a graph of an isolated with an isolated singularity, elliptic linear Weingarten graph, okay, and this manifold, that is the puncture disk, endowed with this metric, recall it is A times, maybe I will write here to recall it. So this is A times the first fundamental plus B, the second fundamental form. This is the disk where your surfaces were defined at the beginning. If this remaining manifold is conformal to a certain puncture disk, that is, if the conformal structure is not of an annulus, then the associated elliptic linear Weingarten graph has an extendable singularity. That is, you will have a well-defined unit normal at the puncture. And moreover, if the surface is convex, that is, if the curvature blows up to plus infinity at the singularity, at the end, you won't have a singularity. The singularity must be removable in this case. So 2 comments before I start with the proof of this removability lemma is that if you want to deal with non-extendable isolated singularities, that is, singularities where the unit normal is not well defined at the puncture, then you will have to consider that this manifold here has the conformal structure of an annulus. Okay, so we will reparameterize the surface with new parameters defined in an annulus. And also, just a comment here is that we don't know in the concave case, that is when the curvature is negative, if those front, at the end you will have a front, you will have a surface where the normal is smooth also at the puncture. But we don't know if this is the case. In fact, the surface has a removable singularity. This kind of elliptic linear Weingarten fronts can exist. The problem is that when you look at in the literature, most of the studies of singularities of fronts are concerning non-degenerate points. But this is a degenerate point in our case, so we don't know if they exist. In fact, if there is an expert on fronts in the audience, I really appreciate any help in this line. So this is the best we can do. A sketch of the proof of this removability result will be the following. Suppose that you have the conformal structure of a puncture disk. That is, you have a conformal diffeomorphism from your original domain, which was the puncture disk, into the unit puncture disk. I have drawn here some pictures to be quickly here. The first step of the proof is that if you have an isolated singularity and the conformal structure is of an annulus, then you cannot have a cusp. That is, the gradient of the solution must be bounded. In some sense, what I am saying that is that the third coordinate, I have called it here M3, the third coordinate of the unit normal cannot go to 0 when we approach the singularity. The way we prove that is using maximum principle. Recall that M3, the third coordinate of the normal, satisfies this equation here. So if we assume, for instance, that the normal is upward pointing, then M3 is positive, okay, away the singularity, and so this is a superharmonic function. We will consider the minimum of this M3 function on the boundary of the domain. We will call it M0. And now, since we have the conformal structure of an annulus, we can consider a sequence of circles centered at the origin. We have called them CK, and consider a certain solution, the unique harmonic solution, which is 0 at the interior boundary, that is in each of these CK, and constantly M0, that is, those are the conditions, constantly M0 at the exterior boundary of the annulus. And we take the sequence, this by maximum principle, this is a strictly increasing sequence of harmonic functions. And when we take the limit, since H is bounded, the limit solution that I have called here H must be M0, constantly M0. As M3 is always above, at the limit, M3 will be above a certain positive function. So at the end, we deduce that at the singularity, M3 must be positive, and so we cannot have we cannot have a horizontal limit unit normal. So the gradient will be bounded. From that, we can deduce that the area will be finite. We will have a continuous extension of the surface till the puncture. And from that, we can deduce that the normal is in this space, H2, and then some classic results about harmonic maps into the sphere tells me that, in fact, this N will be irregular in the whole disk. So the N, the unit normal, will extend, and by the representation formula, then the whole surface will extend smoothly to the singularity. I must remark that this extension is in terms of the conformal parameters U and V here, which are defined in this puncture disk. To finish, we want to prove that in the convex case, in fact, the singularity is removable. That is because if the curvature blows up to plus infinity, then the Laplacian of the angle function is in this way, where C is a negative function. So C will be a superharmonic function, which is positive. So we can repeat this previous argument we have done with M3 now with C to deduce that this C function, this angle function, will be strictly positive at singularity. So we will have an immersion, and so the singularity is removable. Well, now, let me see, what time is it? Now we will do an asymptotic study of singular or non-extendable elliptic linear Weingarten graphs. We are interested in the case where we do not have an extension of the unit normal to the singularity. So by the previous result, we know that we can reparameterize our surface in terms of conformal parameters for the metric ds² in a certain annulus. You can think in this annulus as a 2π periodic identification of a certain strip. We prefer to work with coordinates in the strip. And here, the red line will correspond to the singularity. It will be mapped into the origin in the original disk where our graph is parameterized. So this is more or less the situation. We will have now parameterization in a certain strip, periodically parameterization. Here, the red line will correspond to the puncture, and we can prove that the surface extends continuously to the puncture, and at the puncture we have a degeneration of the metric ds², and so of the first fundamental form of the surface. Well, why those new parameters, conformal parameters, are good for our computation? The point is that although our surface is not regular, if we reparameterize it in terms of the new parameters, U and V, in this parameterization, X of U and V, recall here, X is just X, Y, and Z, and Z written in terms of these new parameters in this gamma, which is this strip here. With respect to this new parameterization, everything is smooth, in fact, real analytic till the boundaries. If you start with a certain regularity of your graph, we need here K bigger or equal than 3, then everything is analytic across the boundary. Okay? And the proof of this extension result is in some sense technical. I'm just going to give a brief notion of what is the proof. We first note that the normal belongs to the Sobolev space, so we can extend it continuously to the boundary of our strip. Then we will apply hence result to the Laplacian of this normal, and we obtain this higher regularity not only in the interior of the domain but also to the boundary. Here this B epsilon is just a ball of radius epsilon centered at one point of the real line where the singularity is. You can repeat this procedure at each point of the red line corresponding to the singularity, and so you obtain this kind of regularity along all the real line. Later, you can do a bootstrapping or recurrence method to attain more regularity to n and also to x. So you achieve C2 alpha, and once you achieve this kind of regularity, some boundary regularity result concerning analytic functions tells you that everything is analytic across the boundary. So as a corollary of this extension result, we can say that the unit limit normal, we call that it would be the restriction of the unit normal to the points which have V coordinates coordinate equal to 0. This will be the definition from now on. This curve, this unit normal, this limit unit normal, is in fact a real analytic Jordan curve. And since we started with a graph, will be contained in one of the closure of the two hemispheres. It will be in the upper hemisphere or down hemisphere. And moreover, by analyticity, we know that the zeros of the third coordinate of the normal will be isolated, or it is constantly zero. So at the end, we can say that or this limit unit normal is the equator that we are calling here as E, or it will touch the equator at isolated points. So this is something I wanted to say. As a consequence of this extension, you know that when you start with an elliptic linear Weingarten graph with an isolated singularity, you can go across the singularity. When you go across the singularity, that is when you reflect your domain. Here I have painted in yellow the upper part, and in green the down part. The yellow part will be parameterized, and this concave part upstairs, and this green part will be parameterizing this convex part downstairs. This is a revolution, this is a rotational example, but in general, for any graph that you start, if you assume that the singularity that your reflected surface has is isolated, you can prove that the reflected one will have opposite sign of Gaussian curvature. So if you start with concave, you obtain convex, and conversely. And also, since you are assuming that the metric d squared here upstairs is positive defined, downstairs this metric is negative defined. So downstairs you must change the orientation and change the sign of A, and you will obtain also a Riemannian metric, the same Riemannian metric associated. Here the constants A and B are equal for both surfaces. An important technical remark is that if you start with a convex graph, you immediately know that the reflected or extended, I don't know what is the best word to use, the reflected surface will be concave and also with one isolated singularity. But if you start with a concave surface, as this is the case, not in the rotational case, because in the rotational case everything is wonderful, but in general, if you start with a concave non-rotational surface, you cannot assure that when you reflect, the reflected surface has an isolated singularity. Maybe you will have curves of singular points crossing at the puncture. So we want to avoid this kind of situations, since, as I have said before, we do not control the behavior of singular points of fronts in our family. So the most important result concerning the asymptotic behavior of the unit limit normal of our surface is the following lemma here. It says that up to a small rotation, if you start with an elliptic linear Weingarten graph, and you suppose that its parameterization, extended parameterization, I have said, you know, everything extends across the boundary. If this whole double surface has an isolated singularities, only two situations are possible. The first one is that the limit normal is a regular, negatively oriented, strictly convex Jordan curve. This negatively oriented is just a question. A technical question is that the geodesic curvature of the limit unit normal is strictly negative, as geometrically it's nothing but a strictly convex Jordan curve in the sphere. That is, I recall. Or you have this limit unit normal, which is a strictly convex curve in one of the hemispheres. That is, your curve does not touch the equator, or it is exactly the equator. Okay, you have only these two situations. What is the proof? The first step of the proof is to see that this limit unit normal is in fact a regular curve. That is, that the norm of its tangent is different from zero. If you parameterize everything in terms of these orthogonal parameters, which are conformal, you see that since the angle function is equal to 0 at the singularity, this norm is different from 0, so your curve is regular. After that, we see that there is this relationship between the geodesic curvature of the limit unit normal and the normal derivative, that is the vertical derivative of the angle function. CV, you can see it's the vertical derivative when you go away the singularity. As you know that the angle function is identically 0 along the real line and is strictly positive on the upper part of the strip, then you will deduce that this normal derivative must be non-negative. Now, in particular, you can say that your curve will be convex. Moreover, by analyticity, you know that the zeros of this geodesic curvature will be isolated, or this geodesic curvature will be identically 0. If the geodesic curvature is identically 0, it's because your limit in the normal is the equator. This is one of the possibilities in the statement of the lemma. In other case, you know that the points where this geodesic curvature vanish are isolated. Well, the point is that if the curvature is positive close to the singularity, then we know that the angle function is a superharmonic function because C is negative here. So Hoff's lemma asserts that this normal derivative must be positive along the real line. So you won't have points of 0 geodesic curvature here. The problem is that if your surface is concave, here the inequality points in the wrong direction, because if the curvature is negative, C is positive. C is positive, so this is a subharmonic function, and C is positive. But as I have said before, in this case, you can look at the reflected surface. You can look at the reflection of the angle function. When you reflect the angle function in the down part of the strip will be negative. So you will have a negative subharmonic function. You can apply again Hoff theorem of lemma. To finish the proof of the lemma, we want to see that our curve cannot touch the equator, or it is exactly the equator. The case that it is exactly the equator, we have already talked about. But in the case it is not exactly the equator, we know by analyticity that the points where the third coordinate of the normal are 0, that is when the normal becomes horizontal, must be isolated. But as the limit unit normal is a convex surface, a convex curve, these touching points must be one of them. You cannot have more than one contact point with the equator. If this is the case, you can do a small rotation, as I have shown here in the picture, and you can undo the situation. What I want to say is that if you have a graph and you know that your gradient blows up at a point, it's not that your surface is not good, it's that you have a bad parameterization. You can change a little bit the parameterization and you will have a limit tangent count. You won't have a cusp anymore. Okay, and that finished the proof of this lemma. So let me show you how to construct singular solutions. The main assistant theorem I'm writing here was established for general Monge-Ampere equation. I have changed a little bit the statement here because for our case everything is easier since we have a harmonic function. So I have written everything in terms of this normal, which is a harmonic map. It says the following: if you start with a regular negatively oriented, strictly convex Jordan curve, and you put it as initial data for the harmonicity equation in this way, you can obtain a unique solution for the harmonicity equation in a certain strip containing the real line. And moreover, when you construct the surface by the representation formula associated to this n you have constructed in the item, the first item, then this surface will have an isolated singularity if you restrict yourself in the upper half of the strip, this surface that you have constructed has an isolated singularity, and the metric ds square is positively defined, so it is canonic with what we have called canonically oriented. So I'm not going to enter into details, but a sketch of the proof is the following. Just to have the existence of the n is just to a system uniqueness of the n. You just apply the Cauchy-Kowalewski theorem for this initial data. Now you have a normal defined in a certain strip. And since the initial data is a strictly convex negatively oriented curve, recall that we have a relation between the geodesic curvature of the limit unit normal and the transversal derivative of the angle function. So the transversal derivative of the angle function will be strictly positive, negative in this case. So positive. So you will assert that the angle function is strictly positive in the upper part of the graph. So you will have an immersion. The problem is, or not the problem, but what rests to prove is that this graph, this local graph, is in fact a graph. That is, you have an embedded solution. To do that, you have to work a little bit more. You have to perturb your surface by adding a certain paraboloid and then apply Legendre transform and use some topological arguments, and then you obtain that you have a well-defined solution of your Monod equation. Well, since we have done the study of how is the limit unit normal of a singular solution, and we know how to construct singular solutions, we are going to put everything we have done before to obtain together to obtain our classification result. First, I'm going to talk about cusps. As I have mentioned before, we will say that the surface has a cusp if the slope becomes not bounded, becomes vertical. The surface becomes vertical at the puncture. So at the beginning, we could think that the surface may become vertical in some directions, but not in other directions. We didn't know, or it can go to plus or minus infinity, but what we are able to prove is that that is not the case. If you have a cusp, everything is rotational, and everything can be determined explicitly. The cusps are rotationally symmetric. Everything is something like that. And the way to prove that is, as we have seen before, if you have a cusp, that is, if you have any direction when you touch the equator with the normal, in fact, the limit in the normal must be the whole equator. Or you don't touch the equator, or the limit in the normal is the whole equator. So by the uniqueness of the solution of the Cauchy problem for the harmonic equation, if you take this equator and try to construct an elliptic linear Weingarten surface which has this equator as limit unit normal, you will have a unique solution. The solution, you cannot prove a priori that it's a graph, but as we know, there exist graphs, as the one I have shown you before, which the same limit unit normal are the same constants, A and B. The surface must be one of them and must be rotational. The point is that if you start with a linear Weingarten surface and you do a certain normal translation and rescaling, you will always obtain a k equal to 1 surface, as I'm saying here. So you can reverse the procedure. You can start with a rotational k1 surface and translate it and obtain an elliptic linear Weingarten surface and determine when will you obtain a cusp. So you can classify cusps of elliptic linear Weingarten graphs in terms of rotational k1 surfaces, as the one I have presented to you at the beginning. Recall that we have some football, American football ball. So if you think about this ball and you translate, you will obtain the cusp that I have drawn here. And you will have a one-parameter family of these big spheres, so you will have a one-parameter family of these rotational cusps, elliptic linear Weingarten rotational cusps. Okay, so at the end, I think I'm in time, more or less. Sorry, I'm a little bit late, but I'm finishing. This is the main theorem. It's something similar of the case of the inspiration theorem I put at the beginning for the case of pure Munich-Per equation. It says that if you have constants A and B with this constraint, ellipticity constraint, and you call A1 as the class of canonically oriented elliptic linear Weingarten graphs with a non-extendable isolated singularity at the origin, and A2, the class of analytic, strictly convex, negatively oriented Jordan curves in one of the hemisphere joined with the equator, then the map that sends each singular surface in the class A1 to its limited normal gives a one-to-one correspondence. Just a few comments. Here, I assume that the result is local. We are just working close to the singularity, so we identify two surfaces if they are the same in a neighborhood of singularity. Here, this star in isolated means that I'm considering isolated as a global fact, that is, that when you reflect the surface, there is no other curves of singularities collapsing at the singular point of the upper surface. And some final remarks is that I have written here non-extendable. The reason I have written here non-extendable and I have not written simply singularity or non-removable is that, as I have said at the beginning, we don't know if there exists or not isolated singularities of the conformal type of a puncture disk. They will be always with negative curvature. Which are not removable but are extendable. We don't know if that exists. So to avoid this possibility, we have to write it here non-extendable. In the case we could prove that this kind of singularities cannot exist, then you can replace you can erase here non-extendable, and the statement will be more simple. Also, I must point out that if you assume that the surface is convex, this star here is not necessary, and this non-extendable can be replaced by non-removable. Okay? In the convex case, everything is more simple. So I think this is everything I wanted to tell you. Thank you very much for your attention. Sorry for the delay. Can you hear me? I'm
I
sorry.
can hear you. Enrique, are you there?
Hello, can you hear me?
Now we can.
Okay, so maybe the problem wasn't with your audio, it was with my mic. Great. So Asun, we have some questions for you, which were collected during the talk, and I possibly couldn't convey them due to a problem with my audio. So Leonardo, would you like to ask a question yourself?
Yeah, sure.
Answer.
Yeah. In the middle of the talk, you said there was a representation for elliptic linear Weingarten surfaces. Is this representation related somehow to the Weierstrass when the surface is minimal?
The point is that minimal surfaces are not included in this family because they correspond. I will write to you. In some sense, it is, but it's not. It is in the sense that you will have holomorphic functions related to the surface, but it's not the same. I don't know if I can write it here. Observe that the relation that we have is 2 times H plus B K equal to 1. You cannot have H equal to 0 in some sense would correspond to the case you have a 0 here. But in some sense, I don't know what the objective of the question was, but in some sense that the parametrization is recovered in terms of n plus a certain constant, the integral of the derivative of something like that. I may be putting wrong the signals here, but something like that. I think it's a minus here, and the V. And you have some holomorphic functions like this by the harmonicity equation. You know that this function is holomorphic, so it is this one. So not exactly the same. I think I tend to say it's more like Chemotsu type. I don't know. I can tell you the reference, but I think it's not exactly the same because minimal surfaces are not included in the family elliptic case. Okay.
Okay, thank you.
All right. I think Pablo Mira has a question as well.
No, I don't think that.
Yes, I have a question. Asun.
Yeah,
Go ahead.
I will. Go ahead.
Now about the last thing you said about non-extendable. I mean, the problem of whether there are non-extendable singularities.
Mm-hmm.
Yeah. What happens if you take one of those that you don't know if they exist or not, and then make the parallel surface so that it is of constant curvature? Do you still have like an? Maybe you still have an isolated singularity there.
No.
And if you
we have tried that. We have tried that.
You have tried that. What do you obtain?
The problem is that we wanted to avoid this case because we know that since the normal extends and the x extends, the parallel constant mean curvature surfaces must be regular. So we wanted to deduce from that in fact your original surface in some sense will be regular, but we cannot do that because in that case the first fundamental form of the constant I'm going to put constant mean curvature surface is conformal, is something times geometric d squared, right? We want to prove that this is regular.
Yes.
We wanted to prove that this is regular from that, but the point is that this conformal factor explodes.
Oh, okay.
So you cannot control this from this. This depends from K and the H. This is a question of K, of a linear relation between K and H and all this stuff. So this explodes, so this balance.
Okay, I understand.
And
the curvature goes to infinity, right? At the singularity in general.
Yes, okay. Always.
So you cannot control that.
You cannot control that. That was our first attempt, but we couldn't deduce anything from that.
Okay, then I have no suggestion.
It's a pity. What a pity.
Very nice result.
Thank you.
Okay, further questions?
May I ask something, Enrique?
Go ahead, Daniel.
For people that like high dimensions, I mean, do you have any extendable theory? I mean, using all these things come from Pogorelov, right? I mean, from the very old time when he did things like in graphs in 4 dimensions and all that. I mean, can you make a geometric theory in higher dimensions? I mean, graphs in
I hope so. This is a project with the Professor Graham Smith. We want to classify isolated singularities of monopolar equations in higher dimension, but in pandemic times we are on delay, so I cannot say anything about higher dimension. I wanted to know, but I don't know anything yet.
But you're getting to 3, 4, or 5 or generic?
Generic.
I see. Okay, cool.
Thank
It's a
you.
good project.
All right, further questions? If not, then I have a question, which I'm sorry, my mic was kind of bad. I should have asked it before. So I understand. I don't know if the answer is immediate from your extension lemma. Okay, so maybe my question is trivial. Let's give it a try. So you define your singular solutions as solutions away from the puncture with a certain regularity, right? A different way of defining a solution would be a singular solution would be as a boundary point in the space of a regular solution, right? So you could ask for your solutions to be boundary points on, say, the space of CK solutions, right? And then I suspect certainly that boundary would be contained in the definition that you were given, but it's not immediate to me that they're equivalent, right? It's not immediate to me, for instance, that every solution you study emerges as the limit of a sequence of CK solutions.
I don't know if that's true in the space of solutions. You can see it as a limit of translated regular solutions of order A and B, because when you translate, you change A and B, the constants. But I don't know if in the space of regular solutions of the same equation, I don't think if I'm well understanding your question. You mean for the same equation, for the same constants A and B,
yes,
a sequence of regular that evolve to a singular. That's the space. I don't know.
Yeah, I think it might be worth studying, you see, because then, or if that's true, at least maybe up to some conformal change, it would be interesting to see if these singular guys you're studying actually completely describe the boundary of a set of CK solutions. This might even depend on K, right? So it may be a very fine kind of result.
I don't know everything about compactness in this kind of ambience of solution of monopolar equations. I completely don't know. If you have a sequence of solution, how is the behavior of the limit, what kind of convergence you have. I completely don't know. I am a geometric person. I don't know anything about this analytic part. Maybe something interesting I cannot see because I always work with the geometric stuff. So maybe you're right. I really don't know.
Yeah, I think it'll be very interesting to
maybe.
Maybe in the future. Yeah, you know, because it's kind of question that, you know, if the answer is yes, that's great. If the answer is no, you give a counterexample and it's still publishable. So it's kind of question that's interesting, sort of both ways.
You know about this type of convergence of solutions of monopolar equations? You know anybody? You know somebody who works with this part? I don't know anybody who's working with this kind of equations right now.
Yeah. Let me think about it for
yes, I would appreciate yeah. I would appreciate that.
But it's certainly, I mean, the kind of stuff you did certainly motivates this question. So it's a question that's automatically motivated because of what you did.
Of the result, yeah.
Yeah. So
thank you.
Be on the table. Should definitely be there. Okay. Have you got any comments or further questions?
Well, sorry, just one comment about the question you were saying. Maybe I did not understand it correctly, but I'm not sure it can hold in the sense that if this kind of limits with one singularity was this kind of solutions with one singularity was a limit of smooth ones, I mean, you would need to be very careful about the topology that you are using, because what happens is that at some point the smooth part, which would tend to the singularity, let's say the limit unit normal will come from one point to be a complete convex curve. So you will lose like C2 regularity. I mean, just the C2 norm should blow up in some way. So I think you need to be very careful with the topology that you use for that deformation, because CK, I don't think it will be enough. I mean, you need a weaker regularity.
You're absolutely right, and I conjecture it should be L1 lock.
Oh, okay.
Of course, you're right. Of course, yeah.
Okay.
I don't believe this would be true for smooth. No.
Okay.
Yeah. It's very fine. I think there's fine stuff to be done there. I don't think the roughest possible thing will work. Yeah.
Okay, now I understand better now the question.
And that's the point. I was telling, I don't know what is the kind of regularity you have to impose in the convergence. I don't know what the right Sobolev space to consider convergence you have, because I don't know this analytic part of convergence of solutions. I completely don't know. That's the point.
Well, if Graham is looking into this, you might as well tempt him to.
Maybe he's the guy. He's the guy.
He has
I never thought about it.
Yeah. Let's ask him, because he can fit in with some good insights. Yeah.
So thank you.
All right. Cheers.
Yes.
Okay.
We are finished.
Come again? We
are finished.
Yeah. And in that case, let's thank Asun again, please.
Thank you.